Hey everybody, I just want to review some ideas from momentum that we kind of introduced today. So we talked about today how momentum is a physical quantity that has the symbol in physics P, okay? And that's probably a good idea because little m is already taken for mass, so here we have P for momentum. And momentum means mass in motion. So momentum means mass, okay, times velocity. And we know that mass is a scalar, and we know that velocity is a vector, and that means that momentum is a vector quantity. Whatever the sign of the velocity, that's going to be the sign of your momentum because the mass won't contribute a sign. Okay, so if I take a look at an example object here, so let's take a look at one of those small carts in class that we use. So let's imagine we have this small cart and it's 2 kilograms in terms of its mass. Let's say it's moving to the right with a velocity of positive 3 meters per second. To find the momentum, all we need to do is mass times velocity. So the momentum here is 2 kilograms times positive 3 meters per second. And that means that the momentum here is positive 6 kilogram times meter per second. And yes, those are the units for momentum. It's really, nothing fancy here. Okay, imagine if this same car was moving to the left, so the velocity was negative 3, then the momentum would be negative 6. All right, I want to take a look at momentum in terms of these quantities that we've already seen. So if momentum is mass times velocity, that means that we can represent a change in momentum as a change in mass times velocity, right? And if we imagine a case where the mass of the system doesn't change, which is in most cases going to be true, then we can represent change in momentum as m times change in v, right? Now, if I want to think about how acceleration comes into play here, I know that acceleration is equal to delta v over delta t, right? So in terms of delta v, it's equal to acceleration times delta t, right? So if I know that and I think about delta v and I want to substitute in what I have for delta v, I have ma times change in time. And when I think about ma, I definitely think about net force, right? So net force times delta t. And you can write this way as well. You can just write F net times delta t. And this brings us into some pretty interesting quantitative reasoning, okay? So when delta p is 0, F net must be 0. And when delta p is 0, we know that momentum is constant. So when momentum is constant, F net is 0. And I think that this is a big idea. So let's kind of just take a minute here to write this down. If change in momentum is equal to 0, that means that momentum is constant. Okay, constant meaning not changing. And F net then must be equal to 0. And this is actually a very important idea when it comes to momentum because we talk about conservation of momentum, but what we're saying here is that we actually can even have momentum be some constant quantity as long as there is no external net force being exerted on your system. So I just want to take a look at an example problem that we can think about here and just take you through the expert problem solving strategy for momentum. So if we take a look at an example of two carts colliding. When you think about momentum problems, you always want to have an initial state picture and a final state picture. So if we imagine we've got two carts, cart 1 and cart 2. Here's my cart 1 and here's my cart 2. Okay, so I have 1 and I've got 2. And the mass of cart 1 is 4 kilograms. And the mass of cart 2 is 2 kilograms. In the beginning, cart 1 has a velocity, okay, and that velocity is equal to, let's say, 3 meters per second. Now notice here on the velocity I have it v subscript 1 I, and then I stands for initial. And when I come over here, I would have, I'm not going to write the mass again because the mass is the same. I would have V1 final. Okay, so V1 initial and V1 final. Okay, and I don't know what it is. And let's imagine when it hits into cart 2, they stick together. So they stick together and they have some velocity together, but we don't know what that is. So imagine a case where we have this going on. And what's interesting is that V1 final and V2 final, if the two cars are sticking together, they're going to be the same number. Okay, any other quantities that I can find at this point? Well, I definitely know the momentum of object 1 initial. It's just mass times velocity. So in this case, it's just 12 kilogram times meter per second. So imagine this first cart that here, cart 2 here, this V2 initial. Say it's at rest. When an object is at rest, its velocity, so the velocity of object 2 here, initial, its velocity is 0. That means its momentum is 0, because momentum is mass times velocity. And here, I don't know what the final momentum of either of the carts are. So in physics, we like to keep track of momentum with what's called a momentum bar chart. And what I'm going to do is I'm going to show you how you can keep track of a particular system's momentum, okay? Because we know that if we think about a system and no external objects interact with that system, then the momentum is going to be constant. The system I want to think about would be cart 1 and 2 together. And if I think about cart 1 and 2, do any external objects interact with them? Okay, so the answer is no, they don't. So if I consider the momentum of object 1 initial, and I add that to the momentum of 2 initial, I would want to consider any change in momentum, see if I have that, and that should equal the momentum of object 1 final plus the momentum of object 2 final. And most of the time when you fill out these bar charts, you would notice that some of these will come out to 0, and we can simplify the equation and kind of get to work here. So momentum 1 initial is 12. So I want to make a bar, and I consider this my 0 line. Anything underneath it is negative, above it is positive. I want to make a bar that represents 12 kilograms times meter per second. The momentum of object 2 initially is 0. And there is no change in momentum in this system because there's no external objects that interact with my system. On the other side of this equation, I would have some momentum final and some momentum final for this guy. Now here's what's interesting. Do you already know if these momentums are positive or negative? Well, you might not be able to reason to that yet, so I guess that's okay. If they're going in the same direction, though, and the original momentum is 12, then each of these probably have a positive momentum. Another thing I want to ask you is, should the final bars for each of these be the same? Well, if the V final is the same, but the masses are not the same, then whatever the bar is for P2 will be smaller than the bar for P1 because of its larger mass. So let's see if we can write a formula for this based on the bar chart. The bar chart tells us that we have a value for P1 initial. P2 initial is 0, so I don't even need to write that. Delta P, no, there's no delta P, there's nothing external to it. So P1 initial here will equal P1 final plus P2 final. So that's my equation, and that's how I'm going to be able to find my answer. P1 final is going to equal M1, right? M1 times V1 final. P2 final is M2 times V2 final. So this means that 12 equals 4 kilograms times V final plus 2 kilograms times V final. So instead of writing V1 final and V2 final, because in this case these two objects stick together and they have the same V final, I can combine these two terms over here. So I end up with 6 kilograms times V final. I want V final by itself, so I'm going to divide both sides by 6 kilograms. 12 kilograms times meter per second divided by 6 kilograms. The kilograms cancel, leaving you with 2, I'm running out of room over here, leaving you with 2 meters per second equal to the V final. Alright, so what's the final momentum of object 1? 4 kilograms times 2. So this bar should be 8, so not as big as the 12. So even before doing the math for the momentum of the second object, I know that it's 4. Because I know that on this side of the equation, the sum here must equal what was on the left side of the equation. Now we can work it out as well. 2 kilograms times 2 meters per second would give you 4 here. So you can see how this momentum bar chart gives you a visual and just kind of helps you keep track of what you know. So this is our first problem in momentum, and this problem does show us a constant quantity of momentum, but just remember that's only true if net force exerted on your system is 0.